Good afternoon. My name is Jean-Louis Briot. I'm a professor in the Zachary Department of Civil Engineering at Texas A&M University and holder of the Spencer J. Buchanan Chair. Welcome to the 17th Buchanan Lecture. We started in 1993 with Ralph Peck, and obviously now it's a tradition. After a few words of introduction, I will call on Professor John Niedzwiecki, who is interim head of our department. John will give you an update on the progress of our department. Then Professor Chloé Arson will come to the podium. Chloé joined our geotechnical group a few weeks ago. She's from France and received her PhD degree from the École Nationale des Ponts et Chaussées in Paris on advanced soil modeling and numerical simulations. We're hoping that she can help our country in the burial of nuclear waste, among other things. Chloé, it's a pleasure to have you with us. Dr. Arson will introduce Dr. Jean-Pierre Jiru, who will deliver the 2008 Terzaghi Lecture on criteria for geotextile and granular filters. Dr. Jiru indicated to me earlier today that he does have a draft of the written version of his Terzaghi lecture and is willing to send it to anybody who's interested in reading it and giving him some comments. Dr. Jiru is very well known for all his work on geosynthetics and in fact has been called the father of geosynthetics. After a discussion period, Professor Marcelo Sanchez will come to the podium. Marcelo joined our geotechnical group a couple of months ago. He is from Argentina, received his PhD degree at the University of Barcelona in Spain on behavior of unsaturated soils. We're hoping that he can help us in the area of unsaturated soils in general and shrink swell soils in particular. Marcelo, it's a pleasure to have you with us. Dr. Sanchez will introduce Professor Jose Roset, who will present the 17th Buchanan Lecture on the topic of some applications of soil dynamics. Dr. Roset is very well known for his contributions in soil dynamics and has been a tremendous supporter of our program. I'm particularly happy that the Buchanan Lecture Selection Committee chose him for this honor. He joins the likes of Ralph Peck, Jim Mitchell, Jeff Meyerhoff, and many other giants in our field. After a discussion period, I will ask Philip Buchanan to come and give the plaque and honorarium to Professor Roset. Actually, Dr. Roset informed me that he will gift the $1,000 honorarium back to the Buchanan Chair. So we're very much appreciative of your generous contribution to the funds with which we pay for this event. This year was a bad year, as we lost two of our most prominent geotechnical family members. I'm talking about Wayne Dunlap and Lyman Reese, who both passed away a few weeks from each other. Wayne was a great colleague. He taught me about aiming for perfection in geotechnical engineering in general and laboratory testing in particular, which he learned from Alan Bishop at Imperial College. His contributions in the field of offshore geotechnics will continue to help many generations to come. One of Wayne's star projects was the development of the pressurized core barrel. Some of you will remember this, where he would collect samples at depth in the Gulf of Mexico and to avoid decompression of the methane gas trapped in the very soft soil, he had devised a way to close the sampling tube downhole and bring it back to the surface with the sample still at the downhole pressure. He had a bomb on the ship, basically. Then he would take the pressurized sampling tube to the hyperbaric chamber and repressurize the sampling tube and the student to the downhole pressure. The problem was that 1 atmosphere of pressure in the hyperbaric chamber has the same effect on the human body as 1 stiff martini. And they were testing samples at 5 atmospheres. So the conversation between Wayne and the graduate students across the thick glass window of the hyperbaric chamber was really funny. Wayne would say to the student, put the sample in the triaxial cell. And on the other side, in the hyperbaric chamber, the student would look at Wayne and laugh his head off and say, it was so funny. But he was able to demonstrate the significant loss of undrained shear strength of gaseous sediment when you test decompressed samples. We also lost Lyman Rees. I first met Lyman Rees when I visited the University of Texas as a young professor in 1979. He was working on the self-boring pressure meter at the time. We also talked about lateral loaded piles, and I was so impressed to be right in front of the man that had written all those publications that I had used in class during my PhD. His name certainly ranks among the best in the world in geotechnical engineering. He did not talk much, but he sure made a lot of sense. I'm so happy that we invited him to give a special lecture here in 2003. He told us the story about the early days of his work on lateral loaded piles with Hudson Matlock, and we have that on a videotape. I'll be glad to send you a copy of that DVD with my compliments. I would like to ask you to observe a moment of silence in the memory of our 2 colleagues and friends, Wayne and Lyman. This year, there was also some good news. We brought the presidency of the International Society for Soil Mechanics and Geotechnical Engineering to Texas A&M University. I was elected in Egypt about 1 month ago by a vote of 56 countries to 18. I've started to reorganize ISSMGE, but I wanted to talk to you about one special initiative that I have undertaken, the ISSMGE Foundation. During my campaign, I traveled to some 12 countries and talked to a lot of people. One thing became very, very clear. We are very lucky to live in the USA. Our country is rich and free, and many of the things that you and I take for granted, like a paid trip to a conference to improve our knowledge, is an extreme luxury in some countries. One person told me that her monthly salary was $10. So there was no way that she could afford to go to conferences where the registration fee was $700. So I decided to create the ISMGE Foundation. Janet and I have pledged $10,000. Mark Balous, a former student in his company in Lebanon, has also pledged $10,000. The Geo-Institute, as of yesterday, has pledged $10,000. That was at the board meeting. I'm going to ask SMGE to contribute $50,000. DFI has also pledged to contribute, so I hope that you will consider contributing to this very good cause so that other less fortunate geotechnical engineers across the world can experience the kind of things that you and I take for granted. For next year, the best way to find out about next year's lecture is to go to our Buchanan lecture website around September each year. We always host a lecture around mid-November, if at all possible. Now, let me call on Dr. John Niedzwiecki, interim head of the Zachary Department of Civil Engineering at Texas A&M University, to say a few words about our department. I feel very fortunate that the number of geotechnical engineering faculty in our program has nearly doubled in the last 2 years. We were 4, and we're now 7. We now have the potential to rival with the best groups in the country, and we owe that in large part to Professor Niedzwiecki. John?
Thank you. We're very pleased to have all of you here, and we're really excited about the direction of our geotechnical program. Let me tell you a little bit about the department and a little bit about the college. In the last 6 years or so, we've added 112 new faculty positions to the college. Having come from the civil engineering department, I was trying to make sure that a disproportionate share went to the department. And I always worried when they would present the numbers that the other departments would catch on after a while. Fortunately, they didn't. And we're very proud because we have a lot of students. You know, when the whole idea was to reduce the student-faculty ratio and to be competitive, to allow the faculty quality time to think, to work on projects, to work with industry, to excel. And in that time, however, we've become more popular. Our department is nearly 1,600 students in total, and that's a lot, especially when you think of all of the other research activities going on and all of the teaching. And we can't afford to lose anybody, and Dr. Roset, I'm talking to you. that retirement word just doesn't work. I should have said the young and handsome Dr. Roset, because that's what he told me. We're, again, very fortunate that we have the Zachary family that's supported us, and I think if you look at the number of endowed chairs, the number of endowed professorships, there's really not many places that rival this department, and it's due in part to our loyal students and many of them who are here. And it's a message to the ones that are going to be graduating.
Good afternoon. It's my pleasure to introduce Dr. Jiru today. Maybe you wonder what the origin of geotextile or geomembrane was. In fact, Dr. Jiru coined this word about 15 years ago. As Dr. Brio said, Dr. Jiru is considered as the father of the International Geosynthetics Society, as well as the father of the geosynthetics industry. Dr. Jiru first graduated from École Centrale Paris, which is one of our top engineering schools in France, and he got his PhD in Grenoble, in France. He taught geotechnical engineering at the University and the Technical Institute of Grenoble, as well as in École Nationale des Travaux Publics in Lyon. Simultaneously, he was an advisor at the Court of Justice in Grenoble for geotechnical engineering and a consultant to the Disaster Response Agency of the provincial government of Grenoble in the area of civil emergencies. He then worked 5 years for Woodward's Clyde Consultants as the director of Geotextiles and Geomembranes Group. And in 1983, he founded his own geotechnical consulting company, Geosyntec Consultants. In less than 20 years, the number of employees went from 3 to more than 700. And in 2001, he decided to retire, and he's now a freelance consultant. Dr. Jiru designed the first dam incorporating geotextiles, which was constructed in 1970. He developed many of the analytical methods used in geosynthetic engineering for geotextile fibers, geosynthetic drainage systems, unpaved roads, liner system stability and reinforcement slopes, and he also studied the effect of wind on geomembranes and many other fields related to geotextiles. Dr. Jiru has also a strong experience of infield practice. He designed construction procedures as well as testing methods. He gave many expert testimonies for the Court of Justice, and he's also the author of 7 books and over 350 papers, among which many state-of-the-art reviews on granular and geotextile filters, the use of geosynthetics in environmental applications, the use of geosynthetics in dams, and the behavior of geomembranes. He also wrote a huge geosynthetics bibliography, more than 1,700 pages with more than 10,000 references. And Dr. Jiru helped the creation of 2 journals related to geosynthetics, Geotextiles and Geomembranes in 1984, and Geosynthetics International in 1994. He was given the award from the French Society of Engineers and Scientists in 1972. He got the award of the Industrial Fabrics Association International in 1983, and he was awarded by the International Geosynthetics Society both in 1994 and 2004. And in 2005, he was awarded the status of Hero of the Geo-Institute of the American Society of Civil Engineers. Today, Dr. Jiru will present an updated and expanded version of the Terzaghi lecture, which was presented in 2008 for the Geo-Congress of the American Society of Civil Engineers. More than 30 years of work on geotextile and granular filters will be presented. A rational approach to the development of filter criteria will be presented, the application of which will be discussed through the case history of the design, construction, and performance monitoring of a geotextile filter used in a dam. So we are very happy to welcome Dr. Jiru.
Thank you very much for this introduction. As you said, the Terzaghi lecture I will present today is an updated version of the original lecture I presented in 2008 at the American Society of Civil Engineers. But 4 years ago, in 2005, I was very honored to present the Vienna Terzaghi lecture in Austria. And in Austria, the setting was very impressive, and I was using the lectern used by Terzaghi himself 80 years before to present the consolidation theory. And the historic presentation by Terzaghi in 1925 was very dramatic. One of the attendees who disagreed with Terzaghi committed suicide. So feel free to do so if you disagree with me tonight. I never met Terzaghi, and my closest association with him was about 20 years ago. I was presenting a seminar on filter criteria. And at the end of my presentation, an old geotechnical engineer came to me and said, "You remind me of Terzaghi." So I was extremely surprised, and I told him, "I'm very flattered, but why do you say that?" And the old engineer replied, "I saw Terzaghi only once, and like you, he was talking about filter criteria with a European accent." Today, ladies and gentlemen, dear colleagues, I will again talk about filter criteria with a European accent, of course. Work on filter criteria has been published by many authors, and it is not possible to present all of this work in one lecture. And I will only present the work I have done. This doesn't mean that I ignore work done by others, but I had to limit the subject. And the work I've done on filter criteria is essentially theoretical, and in fact essentially done with a piece of paper and a pencil. This doesn't mean that I ignore experimental work. In fact, I do refer to experimental data. But by just doing rational analysis, it was possible to build a coherent system of filter criteria. And I want to present the development of this coherent system because it provides an opportunity to better understand the mechanisms of filtration. And also this coherent system of filter criteria has many practical applications, and I want to make geotechnical engineers aware of those many possibilities. I did this work to improve criteria for geotextile filters, but this work is also applicable to granular filters. And in fact, the first steps of the development of criteria for geotextile filters was inspired by granular filter criteria. As a result, this lecture will often refer to Terzaghis filter criteria. Terzaghis criteria for granular filters are well known. The D15 of the filter should be greater than 4 or 5 times the D15 of the soil. In other words, the D15 of the filter must not be too small, and this is the permeability criterion. The D15 of the filter must be less than 4 or 5 times the D85 of the soil, which means the D15 of the filter must not be too large. This is the retention criterion. The difference between 4 and 5 is not significant. I will use 5 in the discussions. Now, we should note that both Terzaghis criteria are expressed using the D15 of the granular filter. And this is possible because the D15 of a granular material, whether it is a filter or not, is related to the size of the openings of this granular material. And the relationship is that the opening size is about 1/5 of the D15. Now, the opening size of a filter, any type of filter, granular or geotextile, is defined as the diameter of the largest spherical particle that can pass through that filter. In the 70s, several criteria for filter fabrics were used, and some of them inspired by Terzaghis criteria for granular filters. And this is an example of a set of criteria used in the 70s with hydraulic conductivity of the filter should be greater than that of the soil. The opening size of the filter should be greater than 0.15 millimeters, but less than the D85 of the soil. And the open area, which is the ratio between the area of voids and the area, total area of the geotextile, should be between 2 limits. In fact, early on, it was explicitly mentioned that non-woven filter fabrics should not be used. And at any rate, most non-woven fabrics were eliminated by the requirement that the opening size be greater than 0.15 millimeters, which was even worse in an early stage. And at any rate, also, all non-woven fabrics were eliminated by the requirement of a relatively small open area. Progressively, the anti-non-woven clauses disappeared from the criteria. However, the remaining criteria were not satisfactory, as we will discuss. The terminology geotextile appeared in 1977, and it will be used in the rest of this lecture. So in this lecture, I will discuss problems related to the old criteria, present the development of proposed new filter criteria, and discuss the application of the proposed criteria not only to geotextile filters but also to granular filters. Granular filters are well known, so let's see a few examples of geotextile filters. A geotextile filter in a drainage trench, a geotextile filter in a landfill, and a geotextile filter in a dam. So first, let's discuss the development of a permeability criterion for geotextile filters. And we'll also discuss applications to granular filters. The presence of a filter disturbs the flow of water in the soil upstream of the filter. And the selected filter must be such that the disturbance is small and acceptable. Now, the disturbance can affect the pore pressure and the flow rate. Therefore, a permeability criterion should include two requirements: a pore pressure requirement and a flow rate requirement. First, the pore pressure requirement. The presence of a filter potentially increases the pore pressure in the soil upstream of the filter. Pore pressure can have detrimental effects. Therefore, the selected filter should be such that the pore pressure increase is as small as possible and ideally zero. This is the curve of water pressure as a function of depth for water flowing vertically through a soil without a filter. Here is the case with a filter, and we can see that there is an excess pore pressure compared to the case where there is no filter. Now, let's consider the hydraulic conductivity of the filter. If this hydraulic conductivity is increased, the excess pore pressure will decrease, as we see here, until it reaches an ideal case with no excess pore pressure. And if we analyze this pore pressure diagram, we find that the presence of the filter causes no pore pressure increase if the hydraulic conductivity of the filter is greater than the hydraulic gradient in the soil next to the filter multiplied by the hydraulic conductivity of the soil. Here we see typical values of hydraulic gradients in soil next to filters. We see the values are typically less than 2, with the exceptions of some clay liners, and rarely exceed 10 or 20. I said that the permeability criterion should include two requirements, so let's discuss the second requirement, the flow rate requirement. The presence of a filter, even very permeable, decreases the flow rate compared with the case without filter. And calculations done with Darcy's equation show that the flow rate decrease is less than 10% of the flow rate without filter if the following requirements are met. The hydraulic conductivity of the filter should be greater than that of the soil for thin filters, filters with a thickness of 1 to 10 millimeter, and the hydraulic conductivity of the filter should be greater than 25 times the hydraulic conductivity of the soil for a filter thickness much greater, between 250 and 2,500 millimeters. Now, the 1 to 10 millimeter thickness applies to geotextile filters. Therefore, the first requirement becomes the hydraulic conductivity of the filter should be greater than that of the soil for geotextile filters. The other thickness applies to granular filters, therefore the requirement becomes the hydraulic conductivity of the filter should be greater than 25 times the hydraulic conductivity of the soil in case of granular filters. Let's discuss these two requirements. For geotextile filters, by two requirements, I mean the pore pressure requirement and the flow rate requirement. For geotextile filters, the flow rate requirement is more stringent or less stringent than the pore pressure requirement depending on the hydraulic gradient. For granular filters, the flow rate requirement is generally more stringent than the pore pressure requirement because the gradient in the soil next to a filter is generally less and much less than 25. By the way, it's important to note that the flow rate requirement for granular filters can be expressed in terms of particle size instead of being expressed in terms of hydraulic conductivities. Indeed, it is well known that the permeability of a granular material is proportional to the square of a small particle size, D10 or D15 as shown here. This is the classical Hazen's equation, which is a special case of the more general Kozeny-Kármán's equation. Combining the three equations shown here, we demonstrate easily that the requirement that the filter permeability should be 25 times the soil permeability is, in fact, the D15 of the filter greater than 5 times the D85 of the soil, which is the classical permeability criterion from Terzaghi. So this discussion shows that the classical permeability criterion, Terzaghi's criterion for granular filters, is only the flow rate requirement. In other words, it does not include the pore pressure requirement, but it doesn't matter because generally it is more stringent. Therefore, there is a difference between geotextile filters and granular filters regarding the permeability criterion. In the case of geotextile filters, the pore pressure requirement or the flow rate requirement governs depending on the hydraulic gradient, whereas in the case of granular filters, it is virtually always the flow rate requirement that governs, which justifies Terzaghi's permeability criterion. So clearly, to develop an appropriate permeability criterion for geotextile filters, it would have been incorrect to simply imitate the classical Terzaghi's permeability criterion for granular filters. It is true that this classical Terzaghi's permeability criterion provided a starting point for the derivation of a permeability criterion for geotextile filters. However, to extend the work of Terzaghi on granular filters to geotextile filters, it was necessary to thoroughly understand the requirements related to water flow through a filter. Now let's discuss the second filter criterion, the retention criterion. We will show how it can be developed for geotextile filters, and we'll see applications to granular filters. The question is, how should we select the maximum allowable opening size of a geotextile filter to retain a soil. The first simple answer consists of adapting to geotextiles Terzaghis retention criterion for granular filters. The D15 of the filter less than 5 times the D85 of the soil. It is known that, as we discussed before, the opening size of a filter is about 1/5 of the D15 of a filter. So by combining these two equations, we obtain this equation, which gives Terzaghis retention criterion, but expressed in terms of opening size of the filter. This equation means that a filter should only retain large soil particles. Some people think that a filter should retain all particles starting from the very small to the largest one to be sure that everything is retained. Well, that would probably clog. So a filter in geotechnical engineering only needs to retain large soil particles. But this works only if the large soil particles in turn retain smaller particles. In other words, this works if the soil is internally stable. And this is the assumption that was made by Terzaghis, and that is, of course, made when we use Terzaghis criterion. Therefore, an ideal retention criterion should take into account not only the opening size of the filter, but also the internal stability of the soil, because if the internal stability of the soil is not assured, then the filter criterion doesn't work. And therefore, Terzaghis retention criterion is incomplete because it does not take into account the internal stability of the soil. However, Terzaghis retention criterion has been successfully used during decades and decades for granular filters. There are two reasons for the success of Terzaghis retention criterion. The first reason is that, to a certain degree, granular filters work even if the soil is not very stable internally because they are thick. And the mechanism is the following. Particles that are not retained may accumulate in the filter, thereby decreasing the filter opening size until the filter works. In other words, a granular filter adapts itself to the soil to a certain degree. But filter thickness does not explain everything. So the second and most important reason why Terzaghis retention criterion was successful for granular filters is that its use has been limited to the most stable soils. Soils that have a maximum particle size less to a certain value, typically, traditionally 4.75 millimeters, which has led to the practice of the truncation of particle size distribution curves to 4.75 millimeters, a practice that we will discuss later in this lecture. So while granular filters benefit to a certain degree from their thickness, geotextile filters are thin, which has created an incentive for developing a more accurate retention criterion. And naturally, a retention criterion that takes into account the internal stability of the soil. In internally stable soils, there are particles of a certain size that form a continuous skeleton. And this continuous skeleton entraps particles that are a little smaller than the skeleton particles. In turn, those particles return particles that are a little smaller, and so on. This is what happens in an internally stable soil. Therefore, if a filter has openings such that the skeleton is retained, then all particles smaller than the skeleton are retained by the skeleton. And of course, particles larger are also retained, because if a filter retains certain particles, it will of course retain larger particles. But if a filter has openings that are too large and do not retain the skeleton, the soil is not retained because the particles that are retained do not form a continuous skeleton in this case. In conclusion, a filter must have openings such that the skeleton is retained, which leads to two questions. First, what is the size of the skeleton particles? And number two, what is the maximum filter opening size that will retain a skeleton of a certain size? So let's discuss the first question: what is the size of the skeleton particle? And as we just discussed, the skeleton is the essential consideration for internal stability. Internal stability depends on the particle size distribution of the soil, which is characterized by its coefficient of uniformity. And geometric considerations show that in a soil with a coefficient of uniformity of approximately 3, particles are tightly interlocked. In other words, this soil has maximum internal stability. And this is illustrated schematically in the following slides. When a soil has a coefficient of uniformity equal to or less than 3, the coarsest particles of that soil form a continuous skeleton that entraps other particles. But if the soil has a coefficient of uniformity greater than 3, the coarsest particles are not in contact, and therefore they do not form a continuous skeleton that entraps other particles. In other words, when a soil has a coefficient of uniformity greater than 3, the coarsest particles are dispersed and they float in the matrix formed by the other particles. So in this case, obviously, the coarsest particle cannot contribute to internal stability. So in the case of a soil having a coefficient of uniformity greater than 3, we will only consider, for the development of the retention criterion, we will only consider the fraction of this soil that has a coefficient of uniformity equal to 3. In other words, we will ignore the coarse fraction of that soil for the development of the retention criterion, and we will retain only the fraction that has a coefficient of uniformity of 3. This means that we truncate the particle size distribution curve and consider only the particles smaller than Dmax shown here, such that the remainder of the particle size distribution curve has a coefficient of uniformity of 3. But the user of the proposed retention criterion does not have to do the truncation. The truncation is done automatically. In other words, it is included in the equations that express the proposed retention criterion, because the proposed retention criterion is only established using this fraction of the curve shown here, the fraction that has a coefficient of uniformity of 3. So we answered the first of the two questions. We know what is the size of the skeleton particle. Now let's answer the second question. What is the maximum filter opening size that can retain this skeleton that we now know? If the soil is in a loose state, which is traditionally and schematically represented by a cubic arrangement, particles pass through the filter if the opening size is just larger than particle size. But if the soil is in a dense state, represented by an hexagonal arrangement, particles do not pass if the opening size is just as large as one particle size, because a stable bridge develops. So if the soil is in a dense state, particles pass if the opening size is twice as large as particle size. So, based on this simple demonstration, the internal stability of a soil depends not only on its coefficient of uniformity, but also on its density. Now, so far in this lecture, the presentation of the retention criterion has been mostly qualitative. But I have done a mathematical analysis, not shown here, of the role of the coefficient of uniformity and the density of the soil. And calculations lead to the following set of 6 equations. In this table, we see here the role of soil density, and we see here the role of soil uniformity. Now, in this equation, I am not using the coefficient of uniformity, but a linear coefficient of uniformity to keep the equations simple. Now, all geotechnical engineers know the definition of the coefficient of uniformity. The linear coefficient of uniformity is defined using a straight line that closely follows the central part of the actual particle size distribution curve as shown here. So this is the definition of the linear coefficient of uniformity used in the equations. Now, this set of equations can be represented graphically. Here is the graph giving the opening size, the maximum allowable opening size divided by d85 of the soil, and it depends in the abscissa of the linear coefficient of uniformity, and the 3 curves are for 3 densities of soil. And all the curves have a maximum for the most stable soil with a coefficient of uniformity of approximately 3. And the horizontal line in red represents a Terzaghis retention criterion expressed in terms of opening size, as we saw before. There is a significant difference between Terzaghis criterion and the proposed criterion. The proposed criterion is here, Terzaghis criterion here. And in particular, there is a huge difference for a large coefficients of uniformity, in this case using Terzaghis criterion, the red line, allows the use of filter openings that are very large and there is a risk of piping. So therefore, a geotextile filter is safer if it is designed with a retention criterion that takes into account the internal stability of the soil. Now, we can do the same thing for granular filters, and we can adapt this criterion to granular filters. This is what we obtain here. The vertical axis is not expressed in terms of opening size, but more traditionally in terms of D15 of the soil divided by D80, or D15 of the filter divided by D85 of the soil. And Terzaghis retention criterion, therefore, is represented by a horizontal line at ordinate 5. The values provided by the proposed criterion, which are above Terzaghis criterion, may seem unconservative, but in fact, they are consistent with experimental data by Bertram, Sherrard, etc. And we should remember that Terzaghis criterion when it was established based on tests by Bertram, and so Terzaghis had simply made a conservative interpretation of Bertram's test. But the problem, again, is with large coefficients of uniformity, where the proposed criterion is much more conservative than Terzaghis criterion, and we will discuss that again later. And in fact, it is because Terzaghis criterion was unconservative for large coefficient of uniformities that the practice of truncation of the particle distribution curve has been developed, and in fact, truncation is equivalent to artificially decreasing the coefficient of uniformity of the soil. In contrast, the proposed retention criterion is applicable regardless of the maximum particle size. In other words, its use is not limited to particles smaller than 4.75 millimeters. Therefore, the need for the tedious and in fact inaccurate operation of truncating the particle size distribution curves at 4.75 millimeters is eliminated. And in fact, with the proposed retention criterion, remember, the truncation is done automatically. It is needed, but it's done automatically. It is included in the equations. But more importantly, and far more importantly, the automatic truncation takes place at the appropriate location, which generally is not 4.75 millimeters. Therefore, by extending to granular filters the retention criterion that was developed for geotextile filters, we have obtained a tool for designing granular filters that is simpler and safer. Simpler because we don't need the truncation, and safer because truncation is not accurate than the traditional criterion, especially for cases of large coefficients of uniformity. So far, we have discussed the use for geotextile filters of the two criteria that are used traditionally for granular filters, the permeability criterion and the retention criterion. But two additional criteria are needed for geotextile filters. Why? Well, since there are almost unlimited possibilities in geosynthetic manufacturing, it is possible to imagine extreme geosynthetics material that would be unlikely to perform as filters, such as geosynthetics with a few opening punched in a sheet, for example, or some extremely thin, non-woven geotextile. And we need criteria to prevent the use of these materials, and we will see why. Therefore, we need two additional criteria. One, to ensure that the number of openings is sufficient, and one to ensure that the filter thickness is sufficient. So first, let's discuss the criterion for number of openings. And we will see that this criterion that ensures that the number of filter openings is sufficient results, in fact, in a porosity criterion, so we will use that simple name, the porosity criterion. The flow of liquids through porous medium, such as granular filters, fibrous filters, takes place in tortuous channels. We call them flow channels. It is possible to demonstrate that the number of flow channels per unit area is greater in the soil than in a filter that meets the retention criterion for that soil. As a result, the flow of liquid is disturbed at the interface between the soil and an appropriate filter for that soil due to flow concentration. And the disturbance of the flow can cause displacement of soil particles in the vicinity of the filter, which could result in accumulation of fine soil particles at the interface, which could result in clogging of the soil filter system. Therefore, the number of flow channels per unit area should be as large as possible to minimize this disturbance. And there is an additional reason for the number of flow channels in a filter to be as large as possible. Because in spite of the presence of a properly designed filters, there is always a possibility that some particles will move and they may clog some flow channels in the filter. And their impact on flow rate will be reduced if the number of flow channels per unit area is larger. So we have two reasons for wanting a large number of flow channels. And depending on the structure of a filter, the number of flow channels is equal or proportional to the number of filter openings. So a large number of flow channels on large number of flow openings is the same. Therefore, a filter should have as many openings as possible per unit area. It should be noted that many geotextiles are so permeable that even if they have only a few openings, they will still be so permeable that they will meet the permeability criterion. Therefore, the permeability criterion itself is not sufficient to eliminate geotextiles filters that do not have enough openings. Clearly, we need a criterion that is specific to the number of openings per unit area. I do not know a rational analysis of the required number of filter openings. The only guidance I have is we know that granular filters work. Thus, it may be assumed that if the number of filter openings in a geotextile filter is equal to or greater than the number of filter openings in a typical granular filter, then the geotextile filter should work since granular filters work. So it should have a sufficient number of openings. Therefore, the first step of the analysis is to determine the number of filter openings in a typical granular filter. And of course, the number of openings in a filter depends on the geometry of the filter, and we will express the number of openings as a function of a carefully selected geometric characteristic, as a function of the filtration opening size, which is one of the geometric characteristics of a filter, which is linked to others, by the way. Because this will make it possible to objectively compare geotextile filters and granular filters that have the same filtration opening size. Calculations that I will not show here indicate that the number of openings per unit area is approximately 0.1 divided by the square of the opening size of a granular filter. So we will use that as a yardstick to evaluate a geotextile filter. First, a calculation for woven geotextile, which is simple because of the simple geometry of woven fabrics, shows that the number of openings is the relative open area divided by the square of the opening size of the filter. The relative open area is the open area, the area of the holes, divided by the total area of the geotextile. So if we compare that with the preceding equation for granular filter, obviously we find that the relative open area should be 0.1 or greater in the case of a woven geotextile. And this is to ensure that the number of openings in the woven geotextile filter is at least equal to the number of openings in a granular filter having the same opening size. In the case of non-woven geotextile, calculations are more difficult. Only approximate calculation was possible, and I could only obtain a lower and upper boundaries that are shown here. And comparing this equation with the basic equation for granular filter and performing calculation for a wide range of porosities in order to eliminate the porosity parameter from the preceding equation, I obtained a conservative criterion from that range to ensure that the number of openings in a non-woven geotextile filter is at least equal to the number of openings in a typical granular filter having the same opening size. And the conservative criterion is that the porosity of the geotextile filter, the non-woven filter, should be greater than 55%. So in conclusion, for the porosity, for this criterion on the number of openings, we find that for woven geotextile, we need to have a relative open area greater than 0.1, 10%, and for non-woven geotextiles, a porosity greater than 55%. Now, the relative open area of a woven geotextile is the two-dimensional equivalent of porosity. So we can group those two criteria under the terminology porosity criteria. Now, we are surprised now because since the criteria for the two types of geotextile filters, woven and non-woven, are of the same nature, they are both porosity criteria, one may wonder why the numerical values are so different. We want an equivalent two-dimensional porosity greater than 10% for woven filters and 55% for non-woven filters. The reason is that in woven geotextile filters, there is no space lost. All the open space is used for flow. In the case of a non-woven geotextile, there are plenty of blind alleys and there are plenty of volume where the flow is going nowhere, so a significant fraction of the pore space is not used for flow. This is why there is such a huge difference. And in the case of granular filter, it's somewhere in between because it is a random material such as a non-woven geotextile, but the particles take more space than fibers, so therefore there is less space that is wasted for flow. So this is why comparing filters having the same opening size, we have the same number of openings per unit area. If a woven geotextile has a relative open area of 10%, a granular filter a typical porosity of 20–30%, and non-woven geotextile filter 55%. So we understand this ranking now of the three types of filter. Now, the porosity criterion, of course, has never been formulated for granular filters because all granular filters have about the same porosity, so there is no need to establish a criterion for something that is automatic. But for geotextiles, it's another story because we have a wide range of porosity from 1% in some woven geotextiles to 92–93% with some non-woven geotextiles. So a very, very wide range. Many woven geotextiles have a very low relative open area. Many have less than 10%. However, some of them are still used as filters. And I repeat that based on the analysis, woven geotextiles with an open area less than 10% should not be used as filters. For non-woven geotextiles, the requirement is much higher, 55%, but they all meet this requirement because the porosity of non-woven geotextiles is typically between 0.7 and 0.9 in an uncompressed state. And when they get compressed, the porosity decreases, of course, but still remains quite high, 0.6 to 0.8. So they meet the requirement. And in fact, my last comment is useless because I think that in the case of non-woven geotextile filters, the porosity criterion should be applied to the uncompressed state and not to the compressed state, because if you look at a photo of a non-woven, and if you apply a compressive stress on it, you are not going to change the number of openings in the direction of the flow. And the calculations presented were done assuming isotropy of the material, which is, of course, more applicable to the uncompressed state. So clearly, non-woven geotextiles do meet their requirement all the time. So remember, I said we need two additional requirements, one for the number of openings, and the second one to ensure that the thickness of the filter is sufficient. This discussion will be done essentially for non-woven geotextiles. It also applies to granular filters, but it doesn't apply to woven filters because the concept of thickness is not relevant for a woven filter. Now, to understand the role of filter thickness, it is necessary to understand how a particle travels through a filter. And a soil particle that travels through a filter must go through narrow passages called constrictions. In case of a geotextile filter, a constriction is a passage between fibers, and the constriction size is the size of a spherical particle that just passes through a given constriction. Now, a soil particle that travels through a filter moves from one constriction to another one following a filtration path, which is identical to a flow channel. This particle will be stopped or will pass depending on the size of the constriction relative to the size of the particle. So here is a schematic cross-section of a non-woven geotextile filter. The red particle is stopped on the top of the filter. The yellow particles are stopped inside, and the green has managed to go through, has passed through a number of constrictions without being stopped. So let's consider the non-woven material used to make a non-woven geotextile. By material, I mean the bulk material. I'm not considering a layer of geotextile, just a package of fibers. This material is characterized by a constriction size distribution curve. And an important point, by the way, as we will see, is the smallest one, the smallest constriction. This constriction size distribution curve is a characteristic of the material the geotextile is made from. It is not a characteristic of the geotextile. A geotextile, which is this material but with a certain thickness, is characterized by another curve, which is the opening size distribution curve. The first question is, why is there a curve and not a single value of the opening size as we think we have for granular filters? Well, this is a legitimate question because so far we have characterized filters by their opening size, not by curve. We need a demonstration for that. Each filtration path contains a number of constrictions. And a soil particles can go through if it is smaller than the smallest constriction in that path, of course. Therefore, each filtration path is characterized by the smallest constriction in that path. But of course, the smallest constriction in a given path, which we can call the opening size of the path, is different from one path to the other. So therefore, each filtration path has a different opening size. So as a result, a filter is characterized by an opening size distribution curve. If a particle selects a given path rather than another one, it may be stopped or not be stopped because the opening size is not the same in each path. So again, we have indeed an opening size distribution curve. But what is the opening size of the filter? We know it is the diameter of the largest spherical particle that can go through the filter. So, in fact, on that curve here, the opening size of the filter is the top of that curve, but it does not exist in every filtration path. Now, next question. What is the relationship between the opening size distribution curve, which characterizes the filter, and the constriction size distribution curve, which characterizes the material? What is the relationship? We need to do some geometric considerations. in a filter, there is a very large number of filtration paths, millions per square meter. And in a non-woven geotextile filter, due to the limited thickness, in any filtration path, there are not many constrictions, 10 and a maximum 100 with very thick non-woven filters. So statistically, from those two comments, the conclusion is that the smallest filtration path opening size is the smallest constriction size, and the largest filtration path opening size is not the largest constriction size. Therefore, the two curves have the same origin and not the same top. Now, this demonstration may seem a little quick or abstract, so we can redo it with extreme cases. First, limit case, if we consider a filter that has a quasi-zero thickness. In this case, there is only one constriction per filtration path. So in this case, the two curves are the same. The constriction size distribution curve and the opening size distribution curve are the same. Now, the opposite case is a filter that is infinitely thick. The probability for having the smallest constriction of that material in each filtration path is 100%. In any filtration path is 100%. So as a result, all the filtration paths have the same opening size, which is the smallest constriction size. So in this case, the curve is a vertical line starting from the smallest constriction size. So we have two extreme cases, infinitely thick, infinitely thin. And typical non-woven geotextile filters are in between. If it is relatively thick, it will be on the left. If it is relatively thin, it will be on the right. Now, we know that the opening size of a filter is the top of that curve. So it is possible to conclude, if we compare filters made of the same material, characterized by a unique constriction size distribution curve, if we have an infinitely thick material, we have a small opening size. If we have a thick material but not infinitely thick, the opening size will be a little larger. If it is thinner, it will be a little larger, and if it is very thin, it will be larger. So we can see that the opening size increases with decreasing thickness. Of course, a filter doesn't have an increasing thickness. I mean, comparing 3 or 4 filters of the same material but with different thicknesses. So the important conclusion is that for a given filter material, the opening size of a filter made with this material depends on the thickness. So the opening size is not an intrinsic property of the material, but it depends on the material and the thickness of the filter. And in fact, we know in which way it varies. We know it decreases for increasing thicknesses. And this is true for all types of filters, not only non-woven geotextile, but granular filters. But from a practical standpoint, there is a big difference between non-woven filters and granular filters, because granular filters, just for practical reasons, for practical constructions, are very thick, and they have a quasi-infinite thickness, so they are, in the case of infinite thickness, so they have a unique opening size, regardless of their practical thickness, whereas a geotextile filter will have an opening size that depends on its material and its thickness. So far, I discussed this thickness topic in a qualitative way, but I have done a mathematical analysis, obtained this equation that gives the opening size of a filter as a function of the fiber diameter, the porosity of the geotextile, and, of course, the geotextile thickness. This was developed theoretically and has been checked using experimental data with a good agreement. This is represented by a graph. In the ordinate, we have the opening size of the filter divided by fiber diameter. So it is dimensionless, and the abscissa is the thickness of the filter divided by fiber diameter. And consistent to what we just discussed, we can see here that for a given porosity, that is a given non-woven material, the opening size decreases for increasing values of the geotextile thickness. But we can see that those curves tend toward an asymptote, and if we have an infinite thickness, then the opening size becomes a constant value. The same analysis also makes it possible to calculate at least approximately the number of constriction in a filtration path depending on the physical properties of the non-woven geotextile filter. And a parametric study of those curves here show that if we have a non-woven geotextile with more than 25 constrictions in each filtration path, the opening size is not significantly affected by changes in thickness. In other words, in all this pink area, which is limited by a quasi-straight line, which is the area where we have more than 25 constrictions, we are close to the asymptote, and the non-woven geotextile is in a situation which becomes comparable to the situation of granular filter, situation where the thickness is no longer affecting significantly the opening size. So therefore, to be reliable, in order to have an opening size that is not affected by thickness variations, a non-woven geotextile filter should have a thickness that corresponds to at least 25 constriction. And this is the thickness criterion. It is not expressed in terms of thickness, but it is more convenient to express it in terms of constriction, because then it becomes very simple, just a number, 25, independent on porosity and filter and fiber diameter. And this work that I just described, I have learned has been adopted in an ASTM standard on filters. So in summary, we have established 4 filter criteria for geotextile filters: permeability, retention, porosity, and thickness criteria. And the last question is the job finished? I mean, do these 4 criteria form a complete set of filter criteria? Let's think a minute. Filtration is governed by filter openings, of course. The characteristics of openings are the size, the shape, the density, the distribution. The 4 criteria that I just presented address size, density, distribution, but not the shape of the openings. The shape is likely to be irrelevant in the case of materials which have a quasi-random structure, such as granular filters or non-moving geotextile filters, it could be a relevant issue in the case of some woven geotextiles or some other types of man-made filters, perhaps perforated plates with strange opening shapes, perhaps. So perhaps more work is needed on the impact of shape of filter openings on the performance of filters. But in the meantime, I think we can consider the set of 4 criteria as complete, at least for granular and for non-woven filters. Also, I want to say that these 4 criteria form a coherent set of criteria because they address only parameters that are relevant to filtration. Other types of requirements for filters, such as strength requirement, durability requirements, which are important, of course, are sometimes presented as part of the filter criteria. And this should not be, because they are not filter criteria. They are not intrinsic to the filtration function. They can be used for any geotextile function. We always need strength and durability. So I don't want to include those in filter criteria. This is the end of the presentation of 30 years of research on filter criteria. And now we will discuss case history. Case history that has been cited by various authors. It is the case of the first geotextile filter used in a dam. In 1989, this dam was on the cover of Civil Engineering because almost 20 years before, it had been the first dam constructed with geotextiles. Geotextiles on the upstream slope, which is this nice photo, but more importantly, a geotextile filter in the downstream drain of the dam. We see here a photo taken during the construction. You see here the profile of the downstream slope of the embankment dam. You see here the downstream drain, the main drain, and the finger drains also constructed with geotextile filters. And this photo was taken 39 years ago. The dam is 17-meter high, homogeneous dam, silty sand with 30% fines. I was the design engineer, and I could not get adequate sand filter at the last minute. I had to make a quick decision, and I elected to use a non-woven fabric that had never been used as a filter, was not yet called a geotextile. And fortunately, it worked. The dam has been in service since 1970. The performance has been satisfactory. A constant trickle of clean water, a flow rate consistent with the hydraulic conductivity of the soil in the embankment dam, no seepage of water observed on the downstream slope, and a geotextile filter in good condition mechanically, but also with clogging absolutely negligible, because clogging of 0.2% of the pore volume of the geotextile, which is virtually zero, and this was demonstrated by tests on samples of geotextiles removed 6 years and 22 years after construction by nearby university researchers. Now, the outstanding performance can be explained. The first comment is, fortunately, the dam was not designed using filter criteria that could have existed at the time. In reality, I must confess that I did not use filter criteria to select the geotextile filter. I did not know what to do at that time, and I selected the geotextile on the basis of limited experimental data. It had been used on soft soils, and we had some field data showing that there was no apparent penetration, clogging of fine particles, but that was very limited. Therefore, I must confess that some degree of luck was involved in the success of this dam filter, and in fact, without that luck, I would not be here today. 10 years later, I felt compelled to start working on filter criteria because of that luck. So as a result, we can use those filter criteria now for the dam. We have no time to discuss permeability, porosity, thickness criteria. They are very simple to use, and it's easy to check that they are met in this case. We will discuss the retention criterion because we learn much more. This is the particle size distribution curve, a very large coefficient of uniformity, 90. The linear coefficient of uniformity calculated from the red line is also very large, 53. First, let's use Terzaghis retention criterion as written in as a function of opening size. We find 6.4 millimeter. This is very large to retain a silty material, and we know that the problem is caused by the large coefficient of uniformity. We geotechnical engineers know that, and we know that we should have truncated the curve, so let's truncate the particle size distribution curve. Use again Terzaghis criterion, 1.8 millimeter. This is still very large for a silty material, so there is reason to be suspicious. Now, one may criticize the use of Terzaghis criteria because, after all, we have 30% fines. There was virtually no cohesion, but we could use, however, a criterion proposed by Sherrard for soil having a certain percentage of particles smaller than 0.075 millimeter. I used Sherrard's criterion, obtained 2.67 millimeter, still very large. Reused Sherrard criterion with the truncated particle size distribution curve, obtained 0.8 millimeter, still very large for a silty material. It seems that this soil defies all retention criteria. So let's use the proposed retention criteria. We have 6 equations, but here it's easy to select the right one. The coefficient of uniformity was way above 3, and the soil is obviously very dense. It's a dam, it's compacted, so we use this equation. And using it for the D85 and the linear coefficient of uniformity of the soil, we obtain 0.135 millimeter, 0.1 millimeter. That seems immediately more reasonable. Now, as a last check, I will use this same equation with the truncated particle size distribution curve. Well, I told you several times today that this was completely useless because that equation already includes the truncation. Well, let's try anyway. So we truncate. We know that the D85 becomes 1.8. The linear coefficient of uniformity becomes 25. We apply the equation. We obtain 0.135. We obtain the same result. Of course, we knew it because we knew that truncation was already done. So this remarkable result confirms the validity of the proposed retention criterion. So clearly, the tedious and inaccurate operation of truncation is not needed with this criterion. We showed it on one example with a geotextile filter. We could have shown the same thing with a granular filter. And so in conclusion, we can say safely that the required value of the opening size is 0.135 millimeters or less. This seems more reasonable than the other values that we obtained. The actual opening size was not measured 40 years ago, but was measured on samples taken from the dam. The lab found 0.1 millimeter, which just meet the retention criterion, which is fine. By the way, we can play a little game and calculate the opening size because we know the characteristics of the filter from simple measurements. And we have this equation that I presented earlier, so we can use it with this characteristic, porosity, fiber diameter, density, etc. And we find 0.099 millimeters. It's almost too good to be true, but this is what it is. So this is in very good agreement with 0.1 millimeter. In fact, this equation is very useful because it's much simpler to calculate an opening size than to measure it, especially knowing that the methods used by many laboratories are very crude and opening size results are often questionable. Furthermore, using that equation, we can predict what would be the opening size of a filter inside an embankment under compressive stress, because it's very easy in the lab to do a simple compressive stress, measure the porosity of the geotextile, and calculate what would be the opening size under stress. I did not do it here. Of course, it would be a little smaller, which would even better meet the retention criteria. So the conclusion of the case history is that the geotextile filter has performed well since 1970, and the 4 criteria are met, which is consistent with the good performance. So in summary, we have reviewed the 2 classical filter criteria, the permeability criterion and the retention criterion, for both granular and geotextile filters, and we have added 2 criteria, porosity and thickness, for geotextile filters. The conclusion for geotextile filters is that the 4 proposed criteria form a coherent set of criteria that allow safe design of geotextile filters. The conclusion for granular filters is that the retention criterion for granular filter can be improved, as we saw, based on development that were made for the retention criterion of geotextile filters. Therefore, what started as technology transfer from geotechnical engineering to geosynthetics engineering has resulted in technology transfer from geosynthetics engineering to geotechnical engineering. So I'm sure that Terzaghi would have agreed that his famous filter criteria were not frozen forever, but rather could lead to new developments. And I'm sure that Terzaghi would have agreed that with a new filter material, the geotextile, it was not sufficient to simply adapt his criteria, but it was necessary to review the fundamentals of filtration to develop a new criteria for those new materials. So just imitating the great masters is not the best approach to solving modern problems. We do not have to do today what Terzaghi would have done 50 years ago. We need to do today what Terzaghi would do today. Thank you.
Thank you very much, Dr. Jiru, for a very clear and very useful lecture. I have a certificate of appreciation for you. It says, Certificate of Appreciation to thank Dr. Jean-Pierre Jiru for delivering the 2008 TUSAG lecture entitled Criteria for Geotextile and Granular Filters at the occasion of the 17th Buchanan lecture, November 13th, 2009. By the way, Friday the 13th is a lucky day where I come from. Yeah. Thank you very much. Thank you. Thank you. Thank you.
Good afternoon. Buenas tardes. Welcome to the 16th Spencer Buchanan Lecturer. I am very happy and very pleased to introduce our speaker, Professor José Roset. He's very well known for most of you, but let me introduce some few words about his career and main achievement, especially for the new student here. Professor Roset is a native Spanish with a PhD degree in civil engineering from MIT. He has been a professor at several major universities in the United States, MIT between 1964 and 1978. Then he moved to Texas, University of Texas at Austin, and he worked there for 21 years, and he's with us since 1999. At Texas A&M, he's the holder of the Warford Kane Chair in Engineering in Offshore Technology, and currently he's the Associate Department Head of Civil Engineering. Professor Roset's main research interest lies in the area of structural mechanics and dynamics, earthwork engineering, dynamic soil-structure interaction, non-destructive testing, offshore structure, with a special emphasis in fluid structure interaction. Dr. Roset has largely contributed to expand the scientific knowledge in this area. He's very modest, and it's very difficult from his webpage to learn about the number of papers and number of books that he has wrote. But I can tell you that he's the main author and co-author of more than 100 of journal and conference papers closely related to these topics. He's also the co-author of several technical books, including Foundation Vibration Analysis using simple physical models. Professor Roset has been always involved in very challenging problems, pushing scientific boundaries. It is quite difficult to summarize his main contribution. I just want to highlight that he's an expert in nonlinear structure dynamics, geotechnical earthwork engineering, inelastic models, and wave propagation. I think that he has the talent to combine his expertise in these different areas to solve very complex problems involving the interaction between the dynamic behavior of the structure, the soil, and the fluid. Well, he's very well known for his contribution to the design of foundation using a single pile and pile group, considering the soil structure interaction under dynamic condition. Dr. Roset's research also focused on the nonlinear dynamic response of deep water offshore platform and fluid structure interaction effect. He has also contributed to more fundamental wave propagation studies with a special application to the non-destructive evaluation of soil deposit and pavement design. I think that Professor Roset's work is an excellent example of fundamental research applied to solve practical problems of in civil engineering. Examples of that are his involvement in the seismic analysis and design of a nuclear power plant, improvement in pavement design, specifically in flexible pavement, offshore platform, and foundation design. An important part of his research has been conducted for the Offshore Technology Research Center, which is a common adventure of Texas A&M University and UT at Austin. He has been the first research coordinator of the center, then the associated director for UT University, and finally the director at Texas A&M. Well, he's a leading researcher. He's very well known in the United States, but also abroad. He's frequently invited as a visiting professor at UK universities. He's also a professor of the international course in soil mechanics and geotechnical engineering that is organized every year by the SEDEC and La Universidad Politécnica de Madrid in Spain. He's also very well known in Latin America. He's frequently invited as a speaker at the South American Symposium of Structural Engineering. And these are just some examples of his work. Professor Roset is honorary member of the American Society of Civil Engineering and a member of the National Academy of Engineering for his contributions to the analysis and design of dynamically excited structure and structure-soil interactions. I think that is quite impressive. I want to add that perhaps most importantly, Professor Roset has been an excellent advisor and a mentor to most of us. I am just arrived, but I can feel that. I asked his colleagues here about things to talk. I have here a couple of things to add. No, this is a joke. I can say that all of them agree in that Jose is always ready to help selflessly. I would like to conclude commenting about his personality. Jose is a very warm and jovial person with a permanent smile in his face. He's always has the right joke at the right time. And it's a pleasure to work with him. So, as I said, it gives me a great pleasure to introduce Professor Jose Roset, who will present the 17th Buchanan lecture entitled Some Application of Soil Dynamics. Please join me in giving a warm and hearty welcome to Dr. Jose Roset.
Nobody that knows me would recognize me from your description. But that's all right. As you may know, last year, Professor Stocky gave the Buchanan lecture. So after he did, I told Professor Brio, I want equal time. And Professor Brio says, I'll give you equal time on two conditions. One is that I have to be elected president of the International Association, and two is that has to be your last lecture. I agreed, and as you know, he was elected president on a vote that was sanctioned by the United Nations and the ACLU. There was some complaints about the fact that the other candidate was from a minority place or diversity, things like that, but he won fair and square. So here I am. So we're going to talk a little bit about some applications of soil dynamics, okay? Soil dynamics is still out of the mainstream of geotechnical engineering, mostly because most geotechnical engineers have nothing to do with dynamic problems, just as most structural engineers are not involved in dynamic problems, okay? And yet, dynamic problems and dynamic applications in soil dynamics are increasing all the time, and we have more and more of them. So what I would like to do is talk a little bit about some of these applications, and I have selected these ones. I'm going to talk a little bit about vibrations caused by rotating machines, effect of soil on seismic motions, seismic soil structure interaction, soil characterization by geophysical methods, and moving loads. And what I hope to do in the next 2 or 3 hours is to touch a little bit on each one of these topics, give you a little bit of what is the problem, what is being done, and then where are the problems that you still have to worry about when you use the present methods, okay? So let's start with the initial problem, vibrations created by rotating machines. Everything we do in soil dynamics is based on things that were derived over 200 years ago. I mean, things derived by Poisson and Coulomb and Stokes, not Stokes, Stokes. It's one of his ancestors. Anyway, but soil dynamics properly studied in the 1920s, okay? And that was primarily because they were building these types of machines, rotating machines, and in many cases they were having bad vibrations. So in some cases the foundations were failing because of the vibrations. In other cases the people that were operating near the machines were getting home every night doing blah, 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 blah. And that wasn't very good. So they had to start investigating this, and the research, they started having institutes to generate this. And the first research was done by Reisner. Reisner was a professor in Germany. Then he came to MIT. He was there for many years. Then from MIT, he went to University of California, San Diego, where he retired. The research went on in the 30s. In the 40s, there wasn't much research because people were involved with other problems in Europe. Then in the 50s, the research started again, particularly in England at that time. And then in the 60s, it was big in this country, particularly because of nuclear power plants. This is the type of machines, the more modern ones. You see they're in living color now. I want you to notice that those guys there, that's not me. Those are real tall people. So to show you the size of the machine. So what is the problem? These machines rotate because there's an eccentricity between the center of mass and the center of rotation. There's some harmonic forces exerted, and you have vibrations. So the first thing we have to do is try to find out what is the dynamic stiffness of a foundation. If you take a foundation and you put a dynamic load, harmonic load, you're going to have an applied force, you're going to have a displacement, you're going to have an amplitude of the displacement, and you're going to have a phase difference between the displacement and the force. And you all well know that if there is a phase difference, it means that there's loss of energy and there is damping in the system. So out of this, if you do this test, you can find out both a real and an imaginary part of the stiffness, would be P over A cosine phi and P over A sine phi. And what you can do then is represent the foundation, if you want, as a set of springs and dashpots, except that these are not constant springs and dashpots, they're functions of frequency, and that's one of the problems. This depends on the frequency, the values of these things. But anyway, we can do this, and then we can proceed with the analysis. And what I wanted to show you is briefly what happens if you take a matte foundation on the surface of a soil layer of finite depth. If the radius of the foundation is relatively small, say 2.5 meters, and I can't remember what was the thickness of the thing, maybe 20 meters, you have a line, which is the top line there, which is kind of smooth. As you increase the size of the mat, and we go to the dotted line, you see that now it has much more fluctuations. It becomes much more erratic. And all these fluctuations, these are related to the natural frequencies of the soil layer. So each one of these points correspond to a natural frequency of the soil layer. If instead of a matte foundation you have a pile foundation, then you have things like that. If I have a single pile, you have this curve on top, which is kind of smooth. As I go on and I increase the number of piles, what happens is this thing, instead of being nearly constant, now changes quite a bit to its frequency. And if you look at that curve, it's pretty much like a second-degree parabola. And if it's a second-degree parabola, this means that it's of the form A minus B omega squared. So if A is the stiffness K, B can be considered as a mass. And what this means really is that between all those piles, you have some mass of soil which is trapped, and that moves with the foundation. Okay? But the main thing I wanted to show you here is that these things may depend on frequency, and may depend quite a bit on frequency. The damping that you have, you can represent as a dashpot, and the constant of the dashpot is more or less something like this, okay? Which is basically like a constant dashpot. Okay. So that's the first part. Out of this, you compute your dynamic stiffness of the foundations, and then what you want to do is compute now the natural frequency of your foundation, of your mass with the foundation, and make sure that it's not close to the natural frequency of the machine, which is the velocity of rotation of the machine in RPMs, or cycles per second. Let's go now to the second problem, soil amplification of earthquake motions. In the 50s was the first study on this thing, and it was done by Kanai in Japan. And people had observed that the earthquakes that you measured in, or you recorded in California, and the earthquakes that you recorded, for instance, in Mexico City, were quite different. The earthquakes recorded in California were kind of chaotic and had a fundamental frequency of about 2 cycles per second, whereas the earthquakes in Mexico City were very regular, and it was exactly 2 seconds, going on forever. So someone had the idea that maybe this was caused by the soil itself. And out of these, they came out with some basic theories on soil amplification of waves. What is being done normally today, if you go to any important structure, like a nuclear power plant, you are required to find an earthquake for design that is consistent with the soil conditions. And that's what we call site-specific spectra. And what is done typically is to consider that what you have is shear waves that propagate vertically through the soil, and then you have a very simple theory that you all know, and you can find what happens. And you find curves like this one that shows you what the amplification would be. This peak here corresponds to the first natural frequency of the soil. So obviously, if the frequency of the earthquake was the same as the natural frequency of the soil, that would be tremendously amplified. This would be the second mode of the soil, this would be the third mode, and so on. When you go to high frequencies, the thing would be less than 1. So high frequencies get filtered out, but other frequencies are amplified. And that's what we normally do. But there are 2 things that you have to consider. First, you don't have waves propagating vertically. You have waves that come at an angle. And if you have waves that come at an angle, the amplification looks something like this one. And you see that it's almost the same, but the values of the amplification change a little bit. Now, what is more complicated is that you don't have just shear waves. You have combinations of shear and compressional waves. And if you consider those combinations, then you have something like this. This is with combination of SV and P waves. And now what you notice is that the shape is again almost the same, but now you can see that here I have this first peak at the first frequency of the soil in shear. Here I have a little bump, or as Inspector Clouseau would say, a little bimp. And this one corresponds to the first compressional frequency of the soil. And there's some coupling. As the angle of the waves increases, now suddenly this becomes bigger. But what is worse is that now the amplification at this third peak may be larger than the amplification at the first peak. That's what is different. Because at this third peak, you have now a coupling between the compressional motions and the horizontal motions. Okay? And you may get a larger amplification. So these are the kinds of things that they're very hard to implement in practice because you don't know what is the actual frequency content and wave content of an earthquake that is going to occur. Okay, so this is very hard. And that's why we still use shear waves propagating vertically. But what you have to take into account is that not everything can be explained by shear waves propagating vertically, that the problem is more complicated than that. The next thing is that most of what is normally done is assuming linear soil behavior. But we know that the soil is nonlinear. And we have many colleagues here that will tell you that. Soil is nonlinear. So what happens then? What is being done today is do linear iterative analysis, which means you assume some soil properties, you do the analysis, you figure out the strains, based on that you change the modulus and damping, and you repeat until you more or less converge. If you did that, then you would get a curve for a small level of excitation that might be like this for the amplification. For a higher level of excitation, you would get something that would be more like this, but similar. But if you do the true nonlinear analysis, what you find is that this is like this, and is broader than the other thing. Why? Because it does not mean, as it becomes nonlinear, that it has a longer period all the time. The period is changing with time. Okay? So again, we do this kind of nonlinear iterative analysis, but it's an approximation. It's okay, we use it all the time, but take into account this is anathema. But I'm going to tell you that there is no way that a linear system can reproduce, an equivalent linear system can reproduce all the characteristics of a nonlinear system. We would like to believe that it does, but it doesn't, okay? Now, in many cases, it doesn't make too much difference. Okay, let's go to the next one. Dynamic soil-structure interaction. We've seen now that the soil has an effect on the motions that would occur on the free surface of the soil. The next thing is what happens to the structure. Now you put the structure on top of the soil, and now what happens? And you have two types of effects. One is what we call kinematic interaction, and the other is what we call inertial interaction. Kinematic interaction means that if I have a foundation like this, embedded foundation, for instance, the soil is trying to deform like this due to the waves. But the foundation cannot deform like this because it's rigid, and as a result of this, what happens is that the displacement here is less than here, but at the same time I have a rotation. And if you look at that, what you have is something like that. This is the ratio of the translation of the foundation to the translation of the free surface of the soil. And what you notice is that for low frequencies, this is basically 1, but as you go to high frequencies, now there is a filtering of the motions because the foundation cannot deform, and therefore you have a reduction in the motions. This means that if your structure is a relatively flexible structure, it has a small frequency and you're in this range here, the effect is very small. But if you go to a very stiff structure in this range here, and particularly you have a large embedment, then the effect is going to be very large. So typically what happens is that if you have a structure and that structure is embedded, and is embedded substantially, the seismic motions that it's going to experience are going to be much less than if it is on the surface, okay? On the other hand, what happens is that you have some rotation of the base. So the rotation is going to be something like this. What happens with that rotation? Well, you don't like to have that rotation at the base, but whether that rotation is important or not is going to depend on how slender the structure is. If you have a rather stubby structure, it doesn't make too much difference whether you have that rotation. If you have a very slender and tall structures, then that rotation at the base may be bad for you, okay? The next thing is inertial interaction. This is what happened to the foundation. Now we put the structure on top. Now the structure vibrates. As the structure vibrates, it has inertia forces, and therefore it exerts a shear and the bending moment on the foundation, and that makes additional deformations in the soil, and therefore that changes the motion in the soil. And what you have is mainly two effects. A change in the effective natural period of the system. The period becomes longer because it's more flexible. And then a change in the effective damping on the system because you have loss of energy by radiation. And here I have some formulas, not because I want to show them to you, because I know that your grandchildren will like to have them. Okay, now this is the important conclusion. On the left, you see Professor Stocky. He's svelte, blue-eyed, fair-haired. I didn't put the beard, but okay. But you see, nice looking fellow. On the right is Professor Roesset. Short and stubby, etc. For most applications in life, it's much better to be tall, particularly if you want to go to a football game. However, for the case of an earthquake, once you consider the soil-structure interaction, it's much, much better to be short. Because if you look at this, I just sway happily like this when the earthquake comes. But Professor Stocky rocks back, and that's much more dangerous. So please, if anything, remember that. When you consider soil-structure interaction, what it means is if you have very slender structure, you may be mostly rocking, and that's not very good. And you have short, stubby, stiff structures, they just sway happily, you know? Swing. Okay. We go to the next problem, which is soil characterization. There are two, now, in the last 50 years, great emphasis on trying to find soil properties through non-destructive methods, and that's particularly what we call geophysical methods. Okay? And they're based on wave propagation. And there are two things that we can consider. One is methods based on times of arrival. And the idea is very simple. If you give a little impact here, and you measure what happens at this point, and you see how long it takes for the wave to arrive here. From there, you can backfigure what's the wave propagation, and the wave propagation velocity is related to the modulus of the material, so you can backfigure what's the modulus of the material. Let me explain this. In this life, you have some people that have vision, and they have some ideas about things. And normally these ideas are based on relatively simple considerations. You know, I mean, if you do this, that's going to happen, so this should work. And then they go with that thing and they try it, and guess what? It works. And thanks to that, we have progress and we have technological advances and so on and so on. But what happens is that things are always really a bit more complicated than that. So actually you have this idea, it works, but it doesn't work always. So then someone has to come behind and say, well, you know, this is why it works in some cases, and this is why it doesn't work in other cases, and this is what happens. Obviously, the big merit is all the people that have the ideas. Okay, those are the valuable people. That's Professor Stocking, and that's Professor Briot. The other people are the ones that have to do the dirty work or say, well, why does it work on sometimes? And that's me. Okay, so I'm going to show you what happens here. These methods, like the downhole, the uphole, or the crosshole, basically is very simple. You give a little impact, and then you measure in a geophone the arrival of the waves, and then you figure out the velocity. Now, this is a basic idea. If you have a point there and you have applied an excitation which was like this, in this longitudinal direction, and then you had another point along the same horizontal line and you were looking at the motion in the same direction, it's very clear that what you have is a compressional dilatational wave, and this is moving like this, and what you have is a pulse arriving at the velocity of the compressional wave. Okay, this is what happens. If you have the receiver relatively close to the thing, you are going to record something like this, and this time here is exactly the time of arrival of the compression wave. So there's no problem there, but you have this, and you say, well, all I have is a compression wave. If you go a little bit further, you have it this way, and still this works fine. This is the time of arrival of the P wave. But as you move a little bit further, what you're going to realize is that actually this is not a simple pulse. This has a pulse like this arriving at the time of arrival of the compression wave, and then there's another little pulse arriving at the time of arrival of the shear wave. And this is not shear motion, this is longitudinal motion. But what you have to realize is that the basic idea that we have, that if you do like this, you're only going to have compressional waves arriving. That is true if all the points in the vertical plane had exactly the same input applied there. But if you have this at one point, then you don't have a plane front moving. What you have is a spherical front. So in this direction, you have compression waves, but in any other direction, you have a combination of compression and shear waves. And therefore, at some distance, you are going to have both not shear waves, but the effect of shear waves causing motion this way. Okay? Well, this does not affect very much in here, because our interest is in the compressional waves, and the time of arrival of the compressional waves is very clear in any case. But if we go to the next case, we're normally more interested in shear waves and the velocity of shear waves. So now let's say that we have at some point here, we have an excitation like this, and now along this line I have a point and I'm looking at the motion like this. And you will say, well, that's clearly a shear motion. That you have an SV thing, and you have like this, and you're measuring like this, and that's clearly shear. So what I should have is a wave arriving at the velocity of the shear wave, and I can measure the shear wave. Okay, this is what happens. This is at a short distance. This time here is when the motion starts. That's the time of arrival of the compression wave. The time of arrival of the shear wave is here. So the motion does not start at the time of arrival of the shear wave. The motion starts at the time of arrival of the compression wave, even if it is a shear motion. And as I go a bit further away, you see that the same thing happens. This is the time of arrival of the compression wave. This is the time of arrival of the shear wave. Starts here. As you go further out, then it's very clear. I have this little pulse associated with the compression wave, and then here you have very clearly the arrival of the shear wave, and that's the main thing. And as I go further out, suddenly you don't even notice this little thing. All you notice is the shear wave. This is what we call near-field effects. When you go sufficiently far, then this theory is all right, because this spherical front looks almost like a plane front by that time. But if you're very close, then the problem is much more complicated. And people in practice have always fought with this thing and saying, okay, if you have something like this, what is the time arrival of the S wave? Is it here? Is it here? Is it there? Where is it? They don't know. Well, actually, it's here. It's at this time there, okay? But the motion starts before then. Okay? So whenever you have these, you have to be careful. If you're trying to measure shear waves and you're assuming that you have a plane wave front, you don't really have a plane wave front unless you go at some distance. If you're close by in the near field, you are going to be likely to commit errors. Okay, the next type of methods are methods based, instead of on time of arrival, on phase differences, and that's the dispersion curve. And among these, we had the Rayleigh waves, and we had the spectral analysis of surface waves, also called the Stokes method. Okay. Rayleigh waves existed for a long time, and if you go to Rayleigh waves, this is a surface wave, and the basic idea, according to Lamb in 1904, was that the Rayleigh wave propagates now with a given velocity in a half space, which is a constant velocity of the Rayleigh wave, and while body waves decay with the distance, Rayleigh waves, the amplitude decays with the square root of the distance. Okay, now let's see what happens if you do this exactly. This is how the amplitude, this is a bit confusing because what I have here is the amplitude multiplied by the distance, okay? So if this is constant, it means that the amplitude is decreasing with the distance. The amplitude is this constant divided by the distance. If this is like this, with this slope, it means that it varies with the square root of the distance. So you see that in the near field, close to the excitation, this thing is mostly body waves. You don't have a surface wave, you have body waves primarily, and this is decaying with distance. After some time, some distance, now suddenly this becomes closer to the Rayleigh wave, to the theoretical Rayleigh wave. However, notice another thing which is important. If you have Poisson's ratios closer to 0.5, if you have saturated soils, then suddenly this has very large fluctuations like this. You don't start reaching supposedly a theoretical Rayleigh wave until you go quite a bit of distance away. Huh? In this field, this again is near field. In this field, you don't yet have established a Rayleigh wave. The problem is much more complicated than that. And if you look at the phase velocity, at the velocity of propagation of the waves, again, if you have a half space, we are assuming that this velocity is constant, is the velocity of the Rayleigh wave. For a Poisson's ratio of 0, what you have is this. So at some distance here, which is about 2 wavelengths, you have basically nothing. But if you have Poisson's ratio, which is larger and closer to 0.5, now you have these tremendous fluctuations. So now if you measure what the time of arrival at the point here and the time of arrival at the point here, and you try to figure the velocity from there, you may get values which are entirely wrong. Okay? This doesn't matter if you do the analysis of the true solution. If you say, I make an impact here and I'm going to solve the true problem, including everything. But what had been done traditionally is say, I'm going to assume to interpret the data that what I have is a pure Rayleigh wave. And if what I have is a pure Rayleigh wave, I consider there's only one mode of wave propagating, and it's a pure Rayleigh wave. Well, then you're going to have to be careful. And what happens is that you're going to have to go at some distance away to make the measurements, or you're going to be committing errors. Okay. In the original Rayleigh wave method, what happened is that research assistants, also called slaves, used to be cheaper. So traditionally what happens is that the professor was sitting in a little van and had there his TV screen or whatever, and had a little vibrator and was applying the load. And then the slave was moving with his geophone and putting it here. And then he was looking and saying, what's the phase difference? 100 degrees. No, keep moving more, keep moving more, keep moving more. And he was moving until the phase difference was 180 degrees, exactly. Aha, that's half a wavelength. So then you were measuring the distance, half a wavelength is this distance. Then changing the frequency. John, move further. And he was moving, and so on. So it was kind of long, okay? Didn't matter for the professor because he was sitting in the van with a bottle of beer, anyway. But it took a long time. So then Professor Stocky came with this idea of the spectral analysis of surface wave for SASW. And now what you do is you give a short input, impact, and then you have many frequencies at the same time. And now the idea is very clear. Again, if you have very high frequency, your wavelength is small, so you're measuring only what happens in this top layer, and you find the velocity of that layer. If you have now a smaller frequency, you go deeper, so now you measure properties in some range like this. So first you calculate what is the modulus of this thing. Knowing the modulus of this thing, you can go to this thing, then you can go to another frequency, and so on. You can do. As long as this inversion procedure is done with the exact solution, there is no problem. You can do whatever you want. But most of the times, this was done assuming that all you had was a pure Rayleigh wave. And that's where you have some problems, where you have to be careful. So Professor Briot said, could you show some real cases? I only work with virtual things. I never work with real things. Anyway, these were some real cases. This was a soil profile. And in this particular case, this soil profile was very nice. You see that the soil properties were kind of increasing with depth, something like that, in a very smooth way. So if you did the test, and then you back-figure what the properties are in the first simplified form, you were getting this kind of soil properties like this. The experimental dispersion curve was this. The one that you would obtain with those properties was this one, which was good approximation but not exact. And these two results, one is with the exact solution and the other one is assuming a pure Rayleigh wave only. If then you were iterating to converge, say, okay, let's change a little bit the properties, let's try to adjust, etc., then you were coming with some soil properties that were now like this, and then your curve became this. And now you see that you had a very good match. And you see that you could get a very good match to the experimental data, whether you used the exact solution or whether you assumed that it was just a pure Rayleigh wave. But now here we have another case, and this is a bit more complicated. Now in this case, I have a thin layer of soil which is soft, and then a stiffer layer of soil underneath, and then this thing becomes much softer there. So the properties, instead of being increasing always with depth, in fact decrease with depth up to a certain point. If you do that, the experimental curve is this one here. Your first solution using either of the methods gives you something like this, and you see that right here you're missing entirely what's going on in this region. So you fit here well, and you fit here more or less, and here you're missing. If now you correct the thing and you adjust the soil properties to do that, you end up with these soil properties, and then with those soil properties, if you do the exact solution, you get this. That matches very, very well now the experimental curve. But if you did the pure Rayleigh wave, you would get this, that is in fact in worse agreement than before. Okay? So when you come to a case like this, when you don't have a soil profile, the properties are very nice, varying with depth in a smooth way, then it's very important not to assume that you have purely Rayleigh wave, but to do a more exact analysis. Okay, let's go to the last thing, moving loads. There are many problems associated with moving loads, particularly in the last 50 years. You have subways, and you have subways that are being built after most of the town is already built. So now suddenly you're tunneling, and your subway is going to pass very close to the foundations of some buildings. Now, obviously, just due to the tunneling itself, you may cause problems to those foundations, settlements, etc. But even if you don't do during the construction, as the subway passes through, as you have the moving loads, you may be creating vibrations. Now, for most buildings, those vibrations may not be important. But if you have, for instance, a hospital, and someone is in the middle of a delicate operation as the subway goes by, and the person being operated is a lawyer, then you're in problems. obviously. If you have there a plant where they fabricate microchips, where they need great accuracy, and suddenly the thing starts vibrating, there is a problem. And there are many cases like this. There are real cases of hospitals where now suddenly they had a subway passing close by, and what they had to do is change the foundation of the system, put dampers and things like that to prevent the vibrations caused. We have now trains that when they get to a city, instead of, as before, just going through the streets and getting to the station, now they go underground, and that's the same thing as the subway. Okay? What that becomes more significant now is high-speed trains. By the way, I'm sorry to disappoint you. Contrary to what the US government may think, trains like automobiles were not invented in the United States. The first train, the first steam engine train, was a freight train, and it operated in the 1820s in Wales. And it went from a mine to the harbor to carry the ore. The first passenger train started in 1830, between Manchester, UK, not Manchester, New Hampshire, Manchester, UK, and Liverpool. And I don't know if the demand was because there were so many people that wanted to go to the concerts of the Beatles, or because there were all these people that wanted to go to the soccer games between Manchester United and Liverpool, but there was a demand, so they put the train. Few years later, Professor Winkler in Germany came out with a solution to design the rails of a train, and his solution was what has been known as the beam on elastic foundation, or a beam on a Winkler foundation. And basically what they had was a continuous beam over some continuous distributed springs, and the question was how to find the stiffness of those springs, and the stiffness of those springs is what we normally call the modulus of ballast, or the ballast coefficient. Okay? Now those expressions, then you can find an analytical solution, it's very easy, and those expressions are still being used today. They have been used for a long, long time, but what they do is assume that your modulus of ballast is what you would measure under static loads. So again, this is purely statics. Well, if you apply that, this is what you get. And what I'm going to show you is kind of interesting because the same curve up and down. This is putting it versus time. I'm interested in what happens at this point. At this time, the load is here. This is for a moving load, and therefore the displacement at that point is very small. As the load moves, now I start having displacement at this point. When the load is here, this is the displacement at this point. When the load is here, this is the displacement. Then the load goes by, this is the displacement, and so on. But this same solution that shows you how the displacement at one point changes with time is also what is at one time the displacement in space. So if the load is here, this is what the displacement looks like along the rail. And obviously, if you have a train, you don't have just one load. You have to do the superposition of these many loads varying at different rates. This is for a relatively small velocity, say 100 kilometers per hour, or 200 kilometers, if you use the static modulus of ballast. If you have a moving load, it's very much like having a harmonic load, a dynamic load, and you have a critical velocity. And you all know what the critical velocity is because you've all seen supersonic airplanes. Okay? So you have a critical velocity, and if you reach the critical velocity, you have some kind of resonance there. So you have problems. If you use the ballast coefficient that is normally used based on statics, your critical velocity is going to be of the order of 2,000 kilometers per hour. So we don't have to worry about it. But what happens if instead of that we consider this a soil, and that soil has some inertia, and that soil has a dynamic response? And if you do that, as your velocity increases, you start finding something like this. You see, now the fluctuations are much larger, you start getting close to resonance. And this is what I want to show you. This is the coefficient of ballast as a function of the frequency. It's directly related to the velocity, but not one-to-one relation, okay? But if you look at this, you see that as the frequency increases or the velocity increases, this modulus of ballast starts decreasing. So as long as you are at 100 kilometers per hour or less, you are in this range, and it makes no difference what you use. But as you start getting to higher velocities, the modulus of ballast decreases, and as the modulus of ballast decreases, it means that the velocity, the critical velocity, decreases. And for this particular case, if this was an actual case of a soil deposit, that critical velocity was of the order of 450 kilometers per hour. Now, and we already have trains going at 350 kilometers per hour. So now we have some problems with high-speed trains if you start considering soil dynamics, soil effects, instead of just assuming that this is a static problem. Now, there's a lot of research going in this field in Europe right now to try to find what happens. One of the problems that they have with high-speed trains is that in a normal train, you have to do batting of the ballast every few months. Okay, you have the people going there and batting the ballast to compact it. In high-speed trains, they have to do the batting of the ballast every day. So every night they go and they have to do the batting of the ballast. The ballast gets very loose with the high-speed trains. Now, I'm not trying to tell you that that is due only to these dynamic effects. Okay, those dynamics may contribute. Part of the problem is also that as the train goes by, very high-speed train, it creates a suction underneath. So that suction tends to make the ballast loose, and then if in addition you have some dynamic effects, it gets worse. In fact, Professor Gall, who was the mentor of our own Professor Hurlebaus here, was telling us that when they started with the first high-speed trains in Germany, everybody went to the station to see the high-speed trains go. And these were stations where they wouldn't stop. So they were getting to the platform, the train would go by. Yeah? And the people were getting very close to the edge of the platform. And if you were getting very close to the edge of the platform, boom, you were sucked by the train. So imagine what it was to go inside the train and then suddenly, boom, someone with his face against the window on the other side. So that is a proven case, that when you have these high-speed trains, they create a tremendous suction there, and that is proven. So this is another problem which starts becoming very significant. I say there's a lot of research going on. What happens now with high-speed trains when you start considering the effects of the soil, instead of assuming that you just have a ballast coefficient which is constant. Okay, that's all I wanted to tell you.
Jose, thank you very much. Thank you. I feel like a high-speed train just went by. This is a plaque which is recognizing Professor Jose Roset as the 17th Buchanan lecturer, and thanks him for delivering his lecture entitled Some Applications of Soil Dynamics. Thank you very much.
Thank you very much.
It's been a pleasure to be with you.